Okay, so hello everyone again. So in this session, what's the objective? The objective is as follows. We will go through the different parts of the tutorial that I posted, and in order to make this as efficient as possible, instead of just going through the example in the tutorial, what I'm planning to do is go through the examples that we did in class for chapter 12, examples at least 12.3, 12.4. And my objectives here is to show you how can we read from an S parameter file, and how can you create just one object with a single S parameters for at one frequency that is given for you. In either case, also show you how can you calculate the different gain circles, whether it's the source or the load, and how to figure out from ADS itself what is the regions of your stability. Is it inside the circle? Is it outside the circle? Calculate the input impedance of a given device, like was done in the tutorial. Show you then how can, after you find out your matching circuit, after you choose your gamma S and gamma L, and you calculate your matching circuits, how can you integrate them in ADS using idle transmission lines if you're not given information about the substrate. Repeat the simulations in the slides or in the notes and get the same answers. So this is, and as we progress, if there's any tips or tricks, I will tell you definitely. If you have any questions also yourself, I will try my best to answer you as per my knowledge and using ADS. As I mentioned in previous classes, that ADS is really a very diverse software. It has so many toolboxes, just like MATLAB, just like ANSYS. So really no one can claim that they know everything about ADS. But you can at least learn what type of learn based on the simulations that you want to run. Okay, so to get started, we will start first by opening again ADS. So I will start by sharing my screen. Sorry, I should have done this earlier. So let me share my screen. I'll share my entire screen. So sorry for any mirrors that you'll be looking at. Okay. So now you look at my screen. So the first thing is that when you start ADS, this is the interface that you expect to see. Now, I would recommend before you begin your work is to create one folder. I call it here ADS, where I'm going to put all the different files that I will work with. Okay, so just to make sure that everything is centralized in one place, because as you work with more and more examples, things might become a bit chaotic. So you start ADS, you go to that a folder that you created. I created it on the C drive and I call it ADS. Then you create a new workspace. So again, file, new workspace. You already know this stuff from the tutorial. Now, for naming the workspace, it's really your call. You can call it anything you want. But to start off with, I'm going to look at example, let's see here, what do I have here? Example 12.1. So I'm going to call this example 12.1. The workspace. Okay, so the workspace is created. So the next step is to calculate or to create your schematic. So file, new, schematic. Now, for the schematic, you can call it whatever you want. So, in this case, let's call it just again example 12.1. I don't think it matters. You can have the same name. I think the only thing that would matter is that the spacing, that the name itself cannot have any spaces in it. So you can use underscores. Now, then you will face the following screen. Now, if you look at example 12.1 in particular, they only give you the S parameters at a single frequency. Maybe I can share this with you here. So this is example 12.1. So you can see that here they tell you the microwave transistor has the following S parameters measured at 1 gigahertz with a 50 ohm reference impedance. So we will use this as our basis here. And they tell you that the source impedance is 25 ohms. The load impedance is 40 ohms. Okay, so this is given for you. So the first thing we're gonna learn here is if you are given a single frequency, how do you put it in ADS? So again, going back to the schematic screen of ADS, for this purpose, if you also check the tutorial that I shared with you, I shared an updated version of it earlier with you. You need to look for a toolbox. So how do you access to the toolboxes? You can access it from here, for example. And you need to look for something called equation-based linear. So again, I'm just scrolling here through the toolbox to find this equation. So this is it, equation-based linear. I hope you can see it. Then over here, you have different options. So I think I need to use the S22. Oh, okay. Oh, this is, sorry. You noticed I did a mistake here. I chose equation-based nonlinear. I should go for equation-based linear. So equation-based linear, again, let me look for it. Okay, it's the one above it. So this is equation-based linear. I select this box as S2, and you have the following. So now here in this box, you need to enter S11, S12, S21, S22, Z1, and Z2. And for that purpose, you need to enter them as complex numbers. Now in the question, they're given for you in polar form, and you need to convert them first to rectangular form. So going forward, so the S11 in the question is 0.38 at an angle of minus 158. So I'm going to do this using the calculator I have here. So again, 0.38 at an angle of minus 158. Again, I'm going to enter it. It is minus 0.35233 minus 0 minus, you can say J to represent a complex number, 0.142351. For S12, again, in the question, it is 0.11 at an angle of 54. So this is 0.0646. Just to save time, I'm going to take everything to 2 decimal places, plus J times 0.089. I'm going to go to the top one, so just take everything to 2 decimal places. And S21, it's 3.5 at an angle of 80. So in rectangular form, that's 0.61 plus J times 3.45. And finally, S22 in the question is 0.40 at an angle of minus 43. And in rectangular form, again, that's 0.29 minus J times 0.27. So again, these are the values in the example converted to rectangular form. Now for Z1 and Z2, this is the reference impedance of the port. It's not the loads, okay? So typically, the reference impedance of the ports is given for you, and it's indeed given in this question. If you look at the question, it clearly states that this is the reference impedance. These are the S parameters with a 50 ohm reference impedance. So, and this is what you need to enter in here. So this is 50 and this is 50. So we are done setting up this block. Now we need to connect the different ports. So in this case, we have nothing else connected. So to connect the different ports for the two bottom ports, okay, you need to ground these. And for the remaining two other ports, this is where your simulation ports will be at. So again, in this case, I need to do an S parameter simulation to calculate the gains and the stability, etc. So for that purpose, you need to go to simulation, S parameters. Now, over here, you have two options. One option is to just use this terminal. So it's a 50 ohm terminal, and then you connect it, of course, to the port. The second option is to use this terminal. I'm going to use it for terminal 2. And then, however, in this case, you need to put a ground to the negative part, and you need to connect the line. Okay? Both either using the first type of terminal, this one, or using the second type of terminal, then you ground the negative part. This is equivalent. Both of these are equivalent. Is it clear so far? Any questions?
No questions, Professor. It's
Okay.
clear.
Good. Now the next part, if you look at the question, it clearly states that ZS is equal to 25 ohms and ZL is equal to 40 ohms, the source and the load. So how is this reflected in your diagram here? So here you need to say that this is the input impedance. It's 25. If I remember correctly, let me go back. So this is 25. The source is 25 ohms. The load is 40 ohms. Okay, so we are done with this. Now, when you set up, this is where you need to put some thought in it. When you set up this way, when you run the S simulation, the S parameter simulation, the S11 that you'll be calculating, okay, from port number 1, in the calculations, this will represent gamma S. If you look at the example we did, we have to calculate gamma S. So this will represent your gamma S over here. So that's the S11 of the simulation, not the S11 of your device. The S11 of your device is given. But for the simulation, when you set the source port to 25, gamma S will be representing your S11. As for gamma L, it will represent your S22 in the simulation. Okay, this is an important thing to keep in mind. So since my ports are not exactly 50 ohms, then the gamma L and gamma S will represent gamma S and gamma L will represent S11 and S22 respectively. So the values we expect from the simulations for S11 and S22 are shown over here. So let's see, is this true? So coming back here, first you need to set up your simulation. So for this purpose, you use this block. Okay. Now in this block, I am doing the simulation at only one frequency. So I double click this. Then I change the sweep type to single point, and it's automatically set at 1 gigahertz by default. So this will be my simulation frequency. Okay, I am done. Then you just press the gearbox to start the simulation. So now it's running. Okay, so hopefully, okay, so now in this case, we don't have to do a plot. We just need to show the data. So to show the data, you need to use this 1, 2, 3, 4, 5, 6 is like creating a list. And unless you have different options. So what I'm interested in is gamma S and gamma L. So it's S11, a gamma S and gamma L, and S22, and it will show you the results by default as a complex number, and it will have a phase and a magnitude. I think you can change if you go to trace options. So if I press trace options here, you have the option to choose it in different ways. Okay, so real imaginary, magnitude and degrees, magnitude and dB in degrees, magnitude radians, etc. So you have different options. You can play around with them. So now I press OK. And this is the results I'm getting. So this is 0.19 and this is 0.66. So it's a bit different than what I expected. S11, S12. I never did this example, honestly. So now I'm just... so the example says gamma L is... so I'm just going to check everything here. So let me double check all my numbers. So,
Professor, could it be that you use two different kinds of terminal ports?
is that
maybe
possible?
The simulation, I don't know, maybe the simulation would need the same kind in one simulation.
I will double check this. So this should be 40. I doubt it, but yeah, the values didn't change. Still 0.19, 0.6. Did I do a mistake in entering the S parameters? I haven't tried this example, so I should have prepared for it earlier. 0. Okay, this is correct. Other one 0.11. 54. This is correct. 0.06. S1, S2, 1. That's 3.5. 0. 1. This is also correct. S22, 0.29. S22 is 0.40. Angle of minus 43. Well, the numbers seem correct. Let me check. So that's 1 minute. So if I change this to 50, if I change this to 50, this will be back to the original values. These are the this 0.37 and 0.369. These are the values. These are the values that that we have in the question. If you look at the question, 0.38 minus 158, 0.40 minus 43. Oh, of course not 0.3. Has anyone tried this example before? These are matched. Okay, so I will need to figure out exactly why is this calculation different than what I expected?
Professor, just a question here.
Yes.
Why are you using the source impedances and the load impedances as the terminal ports? Why not just connect normal resistors and attach 50 ohm ports at the end after those resistors?
Okay, I think
Is that possible?
we can try this out. So what Muhammad is suggesting okay, there are two things here. For the source side, we can try this out. We can connect a resistor. So to connect a resistor, you go to lumped components, you connect a resistor. So this is, and you choose a value which is equal to 25. This is your load resistor. And you keep this as 50. Okay. Now for your load side, I will keep it at 40. And I just want to check how will this affect the values. Okay, so S11 is, again, it's supposed to be 0.11 at an angle of, okay, so this is closer to what we expect. It's supposed to be 0.11 at an angle of minus 180. So no, it's still far away. So for the second one, again, I'm gonna try. This should say 40. Still no. This did not work as expected. It didn't work, Muhammad, unfortunately. This is 0. This is 0. Yeah, of course. Oh, okay. I don't want to keep you on this example. I will try to figure what's the issue here. Sorry for that. I didn't expect this not to work. Maybe I did a mistake somewhere. I need to look for it, and I don't want to waste your time. Okay, so I apologize for it. What I expected, honestly, I'll tell you what I expected. What I expected is that you just need to do the connection shown here. So you connect this port here. No, the same parameters are set to 1 gigahertz, Fawzi, which is the frequency at which we have this example. So this is set already, and I'm double checking this. So yeah, it is set. So this is why I'm a bit confused. What I expected is that this should work to start off with. This is number one. So maybe because the values are not exact.
Professor?
Yes.
I think because when you use the termination, you're setting like the reference impedance for the termination itself. But then like it's taking 25 as the reference impedance. If you can let me show my screen, I'll show you like how it worked for me.
So okay, maybe you can describe it for us.
So yeah, instead of like just adding the termination, I also add like an SP probe. Like if you type in SP, yeah,
Yes.
SP probe.
Okay.
No, it's not this one. It's another one. SP underscore probe. After underscore probe, yeah.
Okay.
Type in SP underscore probe.
Yes, this one.
Yeah, this one.
Yeah.
So like place one in each side basically.
Sorry?
Place one in each side.
Okay. Something
then
I did not
simulate
know
it.
on.
If you like edit the results to show and show like the SP probe, S11, SP probe, all of the SP probe stuff basically.
Okay. Something new. I didn't learn. Okay, good. Thank you, Majid. You saved the day.
No
Okay.
worries.
Okay, thank you, Majid. So honestly, I have not used SP probe before. So for me, this is new. So what Majid suggested, and again, it's always always learn something new here. Placing this SP probe, which I need to read more about it. What does it exactly do? But when you place it there and you set it to 50 ohms, while your load, your source side is set to 25, your load side is set to 40. Then when you display the measurements, you display the measurements from the point of view of the probe. This is why we have 4 different measurements. So I think the first 2 represent the impedances either looking to the left side or to the right side of the probe. And the same thing for the second probe, left side or right side of the probe. Now, if you look at these answers are close to what we have in the slides or in the notes. So the answer that you see here, the first one, this really represents gamma S. So the answer we have in the notes is minus 0.33, which is indeed 0.33 at an angle of 180 degrees. And this is looking to the left side. So it's L. So from this side. While, because, now I think I know what this is doing. And then looking to the right side, this will represent gamma N. So the second one here, so I'll copy this. This represents, let me, some options, this represents gamma N. And then insert again text. This will represent gamma L. And finally, insert text. This will represent gamma out. So thanks, Majid, for finding this out for us. So again, I will post all of this stuff on iLearn, so you can have a look at these different boxes. So again, this is a new box that I just learned. So, and it helps you to calculate gamma S, gamma L, gamma L, gamma S, gamma N, and gamma out as the question requires. So this is something that you can try out, maybe even for some of the assignment problems. I'm not sure if we have one of the assignment problems that you can calculate such a thing. Okay, thank you, Majid, again. And thanks, Subhi and Muhammad, for trying to help out. Okay, so any particular questions about this? So this is the probe that is expected, SP probe. So please try it out. If you have access to ADS, maybe you can also try this out with us at the same time. Any questions? Hopefully this will be better in the next examples. Any questions?
None from me, Professor.
Okay, thank you. Thank you, Subhi. Now moving on, I'm going to go to example 12.2. And again, example 12.2. Let me close this screen. So let me start example 2.2, 12.2. File, new, again, create a schematic. Example 12.2. In this example, we have to calculate, do the stability tests and calculate the stability circles. So what I'm planning to do now, I'm going to do the same thing, enter the S parameters in polar form using the linear equation editor, and then ask ADS to calculate the stability factors and the stability circles, in addition to show us where are the stability regions. So let's start this example together. So again, the same story. I first go and find the equation linear, so which is again equation-based linear. I'm gonna have an S2 port device. I'm gonna put a ground here. I'm gonna put a ground here, and I will go and create my ports. So I'll have my S parameter later on. I need it. This is port number 1. This is port number 2. Now, again, in this example, the simulation is done at a single frequency or a single point, which is 1.9. Let me add this here. Now, the next step, I need still to add my S parameters according to the information which is given for me. So the first one, again, is 0.869 at an angle of minus 159. So this is minus 0. In rectangular form, this is minus 0.81 minus J times 0.31. Then for S12, again, I want to convert it to polar form, so 0.31. The magnitude is 0.031, and this is minus 9. So this is 0.030 or 31 minus J times 0.0049. And for S21, it's 4.250 at an angle of 61. This is 2.060 plus J times 3.72. S22 is 0.507 at an angle of minus 117. So finally 0.23 minus J times 0.45. Now, as for the reference impedances, also the question says that the S parameters are calculated at a reference impedance of 50 ohms. So I added these here. Now, next, to do the stability analysis in ADS, there are different options, and let's go through them. So from the simulation S parameter menu on the left-hand side, we can ask ADS to calculate the mu factor for us, for example. And this mu factor, again, if the number is greater than 1, then the device is unconditionally stable. If it is less than 1, then it is conditionally stable. We can ask ADS to calculate the stability factor for us, which is K. Again, K, if K is greater than 1, sorry, if k is greater than 1 and mu is less than 1, then it is stable. And if k is less than 1, then it's unstable. I can also ask ADS to calculate the stability circles at all the frequencies at which I am running the simulation. So in order to do that, in ADS, we have this box, source stability circle, so I can add it here. I can also do that through the load side. So this is the load stability circle. Then what else do I have? I can ask ADS to figure out which regions of my problem are stable or not. So in order, there are the very last two boxes I have here. SS stability region, I will add it here. And the load stability region, which is, I'm going to also add it there. So let me zoom out a bit to see all the different parameters together. So these are the different simulations that I can ask ADS to do for me. Okay, and also these were covered in the tutorial that I shared with you earlier. Okay, move on. Any questions at this point? Clear? Okay, great. So now I'm going to run the simulation again. So I'm going to press the button here and wait. Okay, so again, we have this empty space. Now, remember, we can show the values. Remember, when we talk about mu and when we talk about k, we need to show their values. Now, another thing that we need to also calculate, but ADS doesn't do this for us, is to calculate delta, which is necessary for the k delta simulation. Now, how can I use ADS to calculate delta? To calculate delta, you can add an equation under the when you have the results page. So you go to equation, you add it anywhere, and then you enter the equation here. So in this case, my equation is, I'm going to calculate delta, or the magnitude of delta, which is equal to, now the notation over here is somehow similar to maybe some of you what you are used in MATLAB. And I mean the notation itself is a bit intuitive. For example, if I want to find the magnitude, you just say absolute. This is the same function we have in also in MATLAB. And then the equation in the slides, it's the absolute or the magnitude of S11 times S22 minus S12 times S21. So now I'm going to recall that I want S11 times S22 minus S12 times S21. Okay, so again, I'm not going to ask you to write complicated equations, except the ones maybe which are already available for you in the tutorial itself. Okay, so you press apply. Okay, if there is no error, it will be clear. If there is an error, it will show up here. For example, let's say if I miss a bracket at the end, you press apply, it will tell you there is an error. Statement separator not expected. So because I missed a bracket. So now this is calculating delta. Now let me display the values of mu, k, and of course for mu, k, and delta in a table. So again, I go to the list. Now over here, I can choose different parameters. For the stability factors, we have mu. I can add it. We have the stability factor, or just k. I can add it. But you'll notice here that there is no delta anywhere. Where is delta? Delta will come under data sets and equations. So if you go to data sets and equations, you have equations, predefined equations, etc. What we are looking for is equations because we created them, and we have delta just there. So we add it to the list. So these are the stability factors. We press OK, and the calculation is shown for us. So again, comparing this to the numbers we have in the example, mu, it was calculated as 0.78. Here is 0.79. So it is unstable or conditionally stable. As for the K delta test, you can see the K is already less than 1, so it fails the test, and delta is less than 1. So S12 absolute of S11, S22 minus S12 times S21. Okay. So any questions to this point?
Professor, here I think the value for delta is different from your example.
Yes,
it is smaller, but it's smaller than 1, but it's different.
Yeah, I just noticed this also. I'm looking at the example. It says it's 0.1130. I calculated as 0.332. Where is there a typo in my equation? Or is a mistake in the 0. Let me check. 0.869 at an angle of minus 159 times 0.407 at an angle of minus 117 minus 0.031 at an angle of minus 9 times 0.40 at an angle of minus 117. If I take the magnitude of this, I'm trying to do the calculation again here. Anyone can see a mistake in the...
Professor, because here we're using the S11, the measurements from the simulation, not the actual S11 from the transistor.
But Majid,
should they be the same?
If I plot the S parameters, so these are the S parameters that the simulation is using. These are supposedly the same ones we have in this.
Okay, they're the same.
Yeah, they're the same ones. So these are the same S parameters that we have also in the notes. So we are using these S parameters. So why is the equation not the same?
I mean, maybe we could try adding an extra set of parentheses before S12 times S21. Or just separating the two.
Oh, you think, okay, we can try to do that. This will be, so it is not, it will be funny if this is the reason. No, it didn't change. Okay, I think I know the mistake. The mistake is in the answer in this in the notes. I'm using my calculator now to do the same calculation, and this is no okay. I figured it out. The answer in the notes is not correct. Or no, actually, let me check. There is in the if I use the same answer in the notes. Okay, give me 1 second. I think there is a typo in the notes, which we just discovered. I will just having a quick look at it. Delta, 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 delta. I'm looking for the delta in the notes. Which slide is it? Okay. I'll tell you what's the absolute of it. Okay. Yes. In the notes, I figured out the mistake. In the notes, or what I'm showing over here, this is delta squared. So let me make a note of it. So what I'm showing here, this one here, this is the whole thing squared. Okay, if you take the whole thing squared, you will get 0.336. Okay, so whatever we did is not incorrect. What we did is correct. It's just that here it's showing the delta squared, not the delta. Okay, is it clear? Okay, so yeah, so our S parameters, these are the ones that we inputted. They are the same. So now thanks Muhammad for pointing this out. Yes, so this delta is correct. The only mistake again is in the slides or in the notes. I'm showing you delta squared, not delta. Okay, so if you take the square
root, Professor, I think so this is actual delta, but in the notes is delta squared for some reason. So when you square
this is correct. Over here, this is correct.
Yeah.
Okay, but in the notes, I said it's shown as delta squared. So I will correct it in the notes.
Okay.
No, so this one is fine here. It's in the slides. It should, again, which is here. I'm showing you delta squared. Okay, so sorry, I will have to remove this parentheses to be consistent. Okay. So I will add this online. So this should say here, if you want to calculate delta, it's the square root of 0.1130, which is 0.336, and this is the same value that we get from ADS. Okay. Clear? So we calculated the stability parameters. Next, let's plot the stability circles. So to plot the stability circles, we need to do it in a Smith chart. So this is the Smith chart tool here. This one, the fourth option. So you show it. Then I want to plot the stability circles. Now for the stability circles, you can see you have different options. What I'm looking for is what will correspond to what's written under as labels for these two boxes. So for this box, the label is stab circle 1. For this box is L underscore stab circle 1. So this is what I need to plot. So L stab 1 and L stab, S stab 1 and L stab 1. So, oops, I did not add it. So L and S, I add them, press apply, and this is what I get. Now, there is a problem here that because these circles, part of them are outside the Smith chart, which is between 1 and -1 for the imaginary part and the real part, as we learned in class, it will try to expand the Smith chart. So we want to prevent this. We want the Smith chart to always be confined between plus and -1. So how can we do that? Again, let me double click on the Smith chart. I go to plot options, and under auto scale, I remove the auto scale option and I set the maximum to be 1. And press OK, and we get the following diagram. And this is the stability circle. So this is the stability circle for this is the stability circle for the load, and this is the stability circle for the source. Now, if I add this information, in a table, so L stab circle, S stab circle, I believe this will give you the values of these circles. So I press OK here. Oh no, this will not give you the values of the circles. So this will give you the values along the circuit. Sorry, this went out. I remember there was an option for it to give you the values of the circles. I haven't tried it for a while, so let's see here. So you can look for it, but there is one option I remember where it can display for you the value for the is it here? No, it's not here. It will display for you the center of the circle and the radius of the circle. If I recall, there was this option. Probably, did I show it in the? I don't have it in the tutorial, so I will look for it. I think there's this option. Doesn't matter. This is what we are after. We are after the stability circles, and it's drawn. Now, the next step is to show whether you are inside or outside the stability circle. So again, I'll go back to 1, 2, 3, 4. And in this case, I need to check the stability region. So for stability region, if I go back to the schematic, I was calculating the stability region using these two blocks. So the labels is S stab region 1 and L stab region 1. So this is what I need to look for here. So L stab region 1 and S stab region 1. I add them, press OK, and you get the following answers. It says for both of them, it says outside. So my stability region will be a point outside the circle. So these are the circles. Any point outside will be in the stability region. And the same thing for the S. Okay? Oops, again, sorry. So this is how you find your, again, this is how you do the stability analysis using ADS. Okay, so any questions? Now, any questions before I move on?
Professor, in the tutorial, you had also used, or you plotted the values of gamma S and gamma L for conjugate matching.
Yes, you can also do that, but I'm just, because here I'm following the example, which example 12.2 in the slides. Okay, because I think here we did not calculate the gammas.
Okay, right.
Okay. Now, which actually brings me to the next, the next thing I want to mention. So let's say that you want to choose your gamma S and gamma L. But again, in this case, you are not, if the device was unconditionally stable, the value of K will be greater than 1. Fawzi, like we studied in the class, the value of K should be greater than 1, and the value of delta should be less than 1. And the value of mu should be greater than 1. Okay, Fawzi? It's exactly like the theory that we studied in class. And in the next example, we're going to show this also. Okay. Yes, you can check. Actually, the first thing you need to do is the K delta test. If the K delta test is satisfied, you don't really need to plot your stability circles, which which brings me to the next point. So if the K delta is not satisfied, this means my device is unconditionally stable. Now, based on this, you have to choose your gamma S and gamma L to be in the stable region. And since you have no gain circles, okay, you can choose it to be any point, and one of these points can just be the center of the Smith chart. Okay, if you choose your gamma S and gamma L, and you design your matching circuits based on that, then exactly the center of the Smith chart will be fine, which means you really don't have a matching circuit. Okay. And this is what we also discussed since we don't in the class. Since you don't have any information about the gain that you are after, then you can choose any point outside the regions for maximum, or sorry, for stability, for your input and output matching. Any questions? Any questions? Is it clear? Zainab, Hala, Ahmad. I didn't hear from Ahmad and Zainab much. Okay. Now, I will move on to example now 12.3. Okay, great. Now, I'll move on to example 12.3. And for this example, the goal here is to design an amplifier for maximum gain at 4 gigahertz using a single stub matching section, and calculate and plot the input return loss. And in this example, again, we're doing stability analysis. We calculate gamma S and gamma L. We calculate some values for GS max, G naught, GL max. So let's work on this example. So to start off with, you will notice here that your S parameters are given in tabular form at different frequencies. So now I'm going to create an S2P file with these values, and I'm going to load these into ADS. So this is the first step that we need to do, is create the S parameter file, and this S parameter file will be read into ADS. Now, I already have prepared one of these files, so let me grab it. So hopefully I have it somewhere here.
And how do we prepare this S parameter file?
This is what I'm going to show you. This is what I'm going to show you. Okay. Okay, Muhammad, that's a good question. So now, the ADS file, first, it will have an extension which is S2P. Okay, you can create it using any editor software. The one I like to use is Notepad or Notepad++. It's just any text-based software. So if I just right-click here and I want to open, I can open with Notepad. There's no issues. Okay. So let me open it. So this is again from Notepad. Now, if you're looking at this file, what I would advise you to do is use the files that I posted online for S2P as your template, just so that you don't have to forget anything. And in this file, whenever you see an exclamation mark, this is a comment. Okay, so an exclamation mark means a comment. It says the file name, and then it says here example 12.P4, but actually it's example 12.3. Okay. Then when you see this number symbol, or I think it's called also sharp symbol in some cases, this will give you information about what are the frequencies that you are at. So it's right now it says it's megahertz. So you can say mega, and then you need to enter your frequencies in mega. You can also, if you want, write it as giga, and then you enter your frequencies as giga. Then here it says you are defining your S parameters. So S, so you have S11, S21, S12, S22. For my S parameters, what am I giving? I'm giving the magnitude given as MA and the magnitude and the angle. This is where it says M and A. So you have the magnitude and you have the angle. So for each of these parameters, I have the magnitude and I have the angle. So the first two will represent S11. The second two will be representing S21, then S12, then S22, in that particular order. So please make sure that your order is correct. Finally, R is the reference impedance, which is 50. Okay, so you need to enter this information. Next, let me bring two files side by side. Also make this smaller. So next, you start giving, again, the magnitude and the angle. So if you read here, for 3 gigahertz, it says 0.8 at an angle of minus 89. So 0.8 at an angle of minus 89. 2.86 at an angle of 99. 2.86 at an angle of 99, and so on. 0.03 at an angle of 56. 0.7 at an angle of minus 41. So this is at 3 gigahertz. Then you repeat the same thing at 4 gigahertz and at 5 gigahertz. So this is how you create your S2P file. Okay, if it's not given for you, you can create it from scratch, as you can see here. Okay, did I answer your question, Muhammad?
Yes, Professor. It's all fine.
Okay, great. So I save it. So let me close this. Then I will go back to ADS. So in ADS, I am ready. This is example 12.2. I'm done with it. So let me close this window. And now I'm going to create a new workspace. This is for example 12.3. File, new, schematic, example 12.3. I created the schematic. Now I want to read my my S parameters from this file that I just created. So for this purpose, again, if you look at the tutorial, what I told you in tutorial, go to search or libraries just here, and look for S2P. And you'll have different options. The one that I'm after is S2P, 2-port S parameter file. Okay, so I select it and I place it here. So this is the one that will represent my S2P. Honestly, I tried to figure out in which toolbox is it exactly, and I didn't find it. So the easiest option for me is just to search for it in under parts over here. So after you are done with this, the next step is to set up your problem. So to set up your problem, for the third port over here, you need to ground it. And then I will put the simulation parameters again. So simulation. And I have one port here, one port there. So let me connect this here, here. And to choose the file, so I double click on this And when you double click, it says, okay, from where do you want your file to be at? So under file name, so you browse where I placed my file. So I placed my file in the ADS folder, so it's here, example 12.3, and I open it. Now, after you enter it, to check, so you keep everything the same. So this is called touchstone format. You keep it the same. Now, if you want to check the validity of your file, you can press here, check view as parameters. And it will show you the S parameter files. If there is an error, also it will show you. So these are the S parameter files that we have. And you can see them. It is given, the magnitude is given for you in dB scale. Okay, I think you can also play around with these to see. This is the angle over here. This is the magnitude and the angle. You can plot it in different types of plots. So this is what we read from the file. And you can see there might be different options here that will help you. Reciprocity, positivity. I haven't used most of them. What I care about is the loaded data, the first option. Okay, so when you are done, you press apply, you press OK, and that's it. So also another way to check that your files are correct, you can run a simulation. So before I start running the simulation, you can limit your simulation to a few frequencies. So let's say I will start at 3 gigahertz. I will stop at 5 gigahertz with a step size of 4, because I have 3 frequencies, 3, 4, and 5. Press apply, OK. Run the simulation. And I can see the tabular data. So S11, S12, S21, S22. Press OK. And you'll get the same data that you started with. Clear so far? Okay. Now, in this example, what we started doing is calculating, before we calculate our the radii of our or not before calculating just our the gammas for a circle, like we have the full procedure. We need to calculate gamma S, gamma L, that will enable us the maximum possible gain. So gamma S is equal to gamma N conjugate, gamma L is equal to gamma out conjugate. We also do a stability test, and we calculate these different values. And this is what we're gonna do next. And this is also what is covered in the tutorial in details. So if I go back to my schematic, so I can do the stability analysis. So I can calculate mu, calculate the stability factor. This is K, so I'll call this K. I will call this just mu. Okay, you can change the names of the labels. Another thing that we will need to calculate is gamma S and gamma L. And to calculate gamma S and gamma L, you can choose the option that Majid showed us earlier, or instead you can use SM gamma 1 block and SM gamma 2 block. And this can help us to calculate the source. So this is the source, gamma source. And this will be gamma load. Okay. You can choose this option, or you can also choose the option that Majid showed us earlier. Okay, so when we are done with this, we can run the simulation again. Now, before I proceed, over here I run the simulation for 3 frequencies, But if you look at the notes, we are doing all this analysis only at one frequency, which is 4 gigahertz. So instead of doing the simulation at all these 3 frequencies, then I will limit my simulation to only 4 gigahertz. So I will go to S parameters setup box again. And for sweep type, I'm going to choose single point. I'm going to say 4 gigahertz. Then I will run it again. So now it's showing me only the S parameters at 4. Now I can also plot the values that I already know. I can plot mu. I can plot the stability factor. Okay, so you can see here, this is also, this matches the answers which are in the notes. So the K factor is 1.195. This is the same one in the notes. The mu factor is 1.04. So my device is stable. What about gamma S and gamma L? So this is represented by SM gamma 1 and SM gamma 2. So I add it, press OK. And this will give me the following table. It will represent the numbers in polar form. So if you check the slides, this is your gamma S, which you have to take the conjugate of it for maximum source gain. And this is gamma L, which you have to take the conjugate of it for maximum load gain. Okay, this matches the answers which are also in the slides, which are shown over here. Gamma S and gamma L. And this is your K and your mu. Now, we will next use ADS to calculate delta and to calculate these gains. And of course, I'm giving the answer here in dB. For that purpose, one way to do it is using the equations again. So I go back to equations. I define my equations. So for the first one, I will calculate delta. So I will copy it from the tutorial just to save on time. So if I go to the tutorial, this is my delta. Just gonna copy it. Control C. Paste it here. Press apply. There's no errors. Excellent. Then I'm gonna create another equation. And I'm going to calculate gamma S maximum. I'm going to create another equation to calculate gamma L maximum. And a fourth equation to calculate gamma naught, which only uses the values of S21 squared, really. And finally, to calculate the gain of the full circuit. So let me here. And this is all in dB scale. Okay, so then I can create a table here to show me all of these. First, for the stability, I'm going to add mu to this table, or not mu, but delta. So if I go to equations, I can just add delta, press OK. And over here, you can see the value of delta has been added. And this is the same value also in the slides or in the notes. Then for the gains, I can create a new table, and I go to equations again, and this is GL, starting with GS max, I can add it, G naught, I'll add it, GL max, I'll add it, and GT max, which is the addition of all of them. And these are the answers in the dB scale. Let me expand this. So at 4 gigahertz, G naught, which is S21 squared, is 8.299 dB, and GL max is 2.21 dB, GS max is 6.2 dB, and finally GT max is 16.7. So this dB, these answers exactly match the ones that we have in the slides, which also is shown here. Okay, so just programming these equations, which is again something which is in the tutorial. Okay, is it clear so far? Now, okay. Now, the next step we have, what is the next step that we did in the problem? The next step that we did in the problem is we took the values of gamma S and gamma L, and we use it to find what is gamma in and gamma out. So gamma in is gamma S conjugate, gamma out is gamma L conjugate, and we use that to create our matching circuits, right? So in this case, we choose an open circuit stub design, and we followed the problem that you can see over here. So one way to do this using ADS is again using the Smith chart tool. So for gamma S, again, we take gamma S conjugate and we're going to go to 50 ohms. For gamma L, we start from gamma L conjugate and we go to 50 ohms. So for this purpose now, I'm going to create, so I'm going to save this first. I'm going to close it. Then I'm going to go here. I'm going to save this. I will copy everything here. I will copy everything. Oops. I will create a new schematic so this schematic I'm going to reserve for the stability and gain calculations. Now I'm going to create a new schematic for the matching circuits. I'm going to paste everything I did here. So if I don't need this anymore, so I'm going to delete them. Now I have two matching circuits. So I will use the Smith chart tool. So where is the Smith chart tool? Or no, wait. I'm not going to use the Smith chart tool. First, before using the Smith chart tool, okay? Before using the Smith chart tool, let's say you don't use the Smith chart tool. You use the MATLAB code that you created for this course to find the values of these sections of the transmission lines. Okay? So you already have the code. It's your code. You get the design, and then, or you can use a Smith chart like the one used here, and eventually you get the following circuit. Okay, which we said that this actually will match the answer that you'll get using the Smith chart tool. So so now this is your implementation, and this is something that I've also seen in the midterm. When I ask you to do something, your implementation, it is the results that you got from your analytical solution or the one that you got from your own Smith chart. It's not like the one that you use the Smith chart tool to do that. So if I want to implement this implementation, this is using transmission lines. Now, in the question, they did not give you any information about whether this is a microstrip line? Is it a coaxial cable? It just told you that this is a transmission line that has a characteristic impedance of 50 ohm, and the length is given for you in terms of lambda. So how I'm gonna now plot these in ADS? So now in ADS, if you don't know what type of transmission line is it, you can assume they are just idle transmission lines. And for this purpose, so let me delete this from here, delete this from here. You need to go and look for transmission lines idle toolbox, which you can see here in front of you. Then from this toolbox, the one that you need to use, at least in this course, is T-line, the first one. And how many do we have of these? We have 4. We have 2 at the input and 2 at the output. So we have 2 at the input. So let me rotate it. When I want to rotate anything, I can use Control R. And 2 at the output. And I build my circuit around them. So let me create some spacing so you can see all the text. And again, I'm just creating so much spacing so you can see all the text. Then I just connect everything using transmission lines. So this will be the input side. This will be the output side. Now you can see that these 2 elements, they are one port for them is not connected. This one and this one over here. So when they are not connected like this, this means they are open circuit. So you just keep them as they are. So I'm just going to center everything in the middle so you can see how the problem look like. Now, for each of these transmission line, I know they have a 50 ohm impedance and their length is given in lambdas. Okay? So let's start with the first open circuit stub. It has a characteristic impedance of 50 and the length is 0.206 lambda. Now, in ADS, you cannot give your length in lambdas, but instead you give your electrical length in degrees. So I need to convert these lambdas to degrees. So how do I do that? Remember one simple thing. 1 lambda is a full wavelength, which will correspond to 360 degrees. So when you say you have 0.206 lambdas, you multiply that by 360 and you'll get 74.16. And you repeat that for all the sections of the transmission line. So this one over here, in the question, it is 0.120 lambda. So 0.120 times 360, that's 43.2. For this section over here, this is 90 degrees, or this is 0.206 lambda again. So this is the same as before, so 74.16. And finally, oops, I should press OK. 74.16. Let's apply OK. And this is 74.16. Now, another important thing is that this is calculated at a frequency of 4 gigahertz. So you can see in all of these transmission lines, the frequency is a parameter. So I need to go back and change all the frequencies to 4. So this is 4. This is 4. And this is 4. Remember, the length of the transmission line is calculated at 4 gigahertz. So now, this over here represents exactly what you have in your notes, which is with the input matching circuit and the output matching circuit. If you want your diagram to look maybe fancy, you can always say, okay, you can create like shapes, like you can create a rectangle. So this is for the input matching circuit. This is for the output matching circuit. You can always insert text. So input matching circuit. And here you have output matching circuit. By the way, one thing that in most of the examples in the class, we use the open circuit stub to calculate the input matching and the output matching circuit. But you can create any type of circuit. You can create, for example, an L network circuit, right? This is the simplest one, like the lumped component one. Nothing is stopping you from doing that, okay? And it's actually will be interesting to do that, because it will show you how it will affect the bandwidth of your device. So now, when I'm done, I need to run the simulation again to reproduce the plot that you can see here. So you'll have G, the gain of the circuit, which is represented by S21, and the return loss, which is the minus of the return loss, which represents the reflection coefficient of the whole system. So now I go back here. I will run now my simulation, not at a single point to get the plot, but I will go from 3 to 5. Now I just have to choose my step size to make sure that I have a plot that will look smooth, not truncated. So I can say maybe 101 points. So this will be gigahertz here. And this is 101. Okay. Fix that. So apply. Okay. Now I run the simulation. Wait for a few seconds or minutes. Okay. So now you get again to plot this again. So I put a plot, and for this plot, I need to plot S11. This will represent minus the return loss, and I need to plot it in dB scale. And S21, which will represent the gain of the whole circuit, and again, I will plot it in dB scale. Press OK. And this is the plot that I got. Now, before you make any judgment about this plot, look back at the plot that we have over here. The plot that we have over here, you will notice that the x-axis is indeed between 3 and 5 gigahertz, but the y-axis is confined between minus 20 and 20 dB. But if you look at your simulation, it is confined between 20 and minus 100. So in order to compare the two plots correctly, and this is something else that maybe I ask you in the assignment and also in the exams, the two plots need to be on the same scale. Both of them should be dB, both of them should be linear depending on the problem. So let me fix the scale over here. So again, how can I do that? I double click on the plot, go to plot options, and you can see you can select the different axes. So for the y-axis, I remove auto scale and I set the minimum to be 20 and the maximum to be the minimum to be minus 20 and the maximum to be 20, and it's a linear scale. I press OK and I get this plot. And now you can see that this plot, and so let me expand this here. These two plots are exactly the same, right? You agree? So again, this is a repetition of the example that we just did we did analytically. You also have the MATLAB code to obtain exactly the same plot, and now we have done it in ADS. Clear? And again, this is the case for the maximum possible gain, which you can see here. If I use a marker, the maximum possible gain is obtained at 4 gigahertz, and it is the expected value, which is 16.6 dB. This is the value that we calculated before. Clear? Move on. Okay. Now, let me expand this a bit. Where's the button to expand? Sorry. Okay. So let me save this. Remember to always save your work. And I can save this. Now, again, another option that you could have done is, instead of doing this circuit, use the Smith chart tool. So, and you can create it even using lumped components, as I mentioned. So let's try this out maybe. So file, save as, say this is circuit, stop. File open. Oops. File open. I'll open this again. I will delete this part. I will delete this part. Then I will insert the Smith chart tool in here. Simulate, where is the Smith chart tool? Smith chart. I'm just looking for it. Oh yeah, here, Smith chart match. Okay. So this is Smith chart tool here. Now, what you need to be careful with when you're inserting the Smith chart tool is your ports. So right now this will be connected to 50, and this will be connected to. So let us give it a try. So connect these here. Connect these here. So let's start with this one. Select it. Go to Tools. Insert. There's the Smith chart. Okay, update from the components. So now here you need, of course, to set this up. So this simulation is done at 4 gigahertz. The reference impedance is 50. Then here you need to define what is your ZL and your ZS. So, okay, so your load, we said, will be at 50. So you lock this. As for your source, sorry, it's the other way around, sorry. Your source will be at 50, and your load will be represented by values of Z that you need to calculate. So what's the easiest way to do this? So, okay, so let's go back here a bit and try to understand this together. So now what I'm planning to go, my load is calculated as Z at Z star conjugate, and I'm going to a 50 ohm source, right? Z as conjugate, and I'm going to a 50 ohm source. Now, what is gamma as conjugate? Gamma as conjugate, which we also calculated using ADS, is 0.8718 at an angle of minus 123.41. So now I need to use gamma as conjugate to calculate my ZS, and ZS will be equal to 50 times 1 minus gamma S conjugate, which is 0.8718 at an angle of 123.41. Actually conjugate, so minus that. So I'll tell you in a second what I am calculating. No, plus, minus. Let me just get the value here in front of me. Divide by 1 minus 0.8718 at an angle of minus 123.41. Okay, so I can get the pen. So now you need to take this value, find gamma as conjugate, which will be 0.87818 at an angle of minus 23.41. Then you need to use this value to calculate what is your equivalent load, I will call it, which is Z naught 1 plus gamma S conjugate divided by 1 minus gamma S conjugate. Again, how can I derive this equation easily? Gamma S conjugate is Z equivalent load minus Z naught divided by Z equivalent load plus Z naught. Okay, so this is what I'm calculating here. So 50 multiplied by 1 plus gamma S conjugate, which is written at the top over here, divided by 1 minus Z at conjugate. Now the answer that I obtained for this one, using my calculator, was 4.41 minus J 26.754. And this is the value that I will enter into the Smith chart tool as my load side. Is it clear what I'm trying to do here? Yes? No? Okay. Ahmed and Zainab? Okay, so now going back to my Smith chart tool. So this is 50 ohms. We fix it at 50. And for my load side, I will set it to the value here, which is 4.41 minus I times 26.75. So you can see this is where my gamma S conjugate is located, and this is what I'm trying to do is reach the center. Now again, you need to use this tool. You can create the same story like you learned before. So I can use. You need to cross this, then you put an open circuit stub. Cross this. So we just move this a bit. So we need to be more accurate. Okay. Something like that. So this is 14 degrees. This is 105. Again, this is one of the solutions. So you can press build using ADS. So now if I go in here, okay. So this is your open circuit stub circuit for the first case. Okay, I think this is one of the solutions again. So because we always have two solutions. So if I go up now, so let me save this. Now you do the same thing for the load side. For the load side, again, go to Tools, Smith chart. Okay. So now I'm doing matching for the second one. 450, 50, so this is number one, number two. So now I need to change. So I will start from the beginning. I'm going to remove this. Delete selected element, delete selected element. Gamma S is still 50, but now I need to calculate my new load. It's not 4.4 anymore. So if I go back to the slides, so gamma L conjugate is 0.8763 at an angle of 61.03 with the minus sign because it's the conjugate. So I will calculate what's the equivalent load here. Again, I'm going to do this directly. Just using my calculator, 63, and this will be 60.03. This will be 8763. 61.03. And the answer that I'm getting is 12.63 minus J, 83.42. Okay, so I'm just double checking my numbers before I move on. This is why there is some silent. Okay, so this is the equivalent load. So now I go back to the Smith chart tool, and for the load side now it is 12.63 minus I times 83.42. Okay, so this is my new point for the conjugate value. Okay, so I'm just checking just to make sure. Now, again, if I want to create an open circuit stub, you can start by an open, then you intersect the circuit, then, sorry, you start with a piece of transmission line, then you intersect, and this is what I get. So again, you can build it and you can go inside and have a look at it. Now, what you need to take care of here is that in the simulation that we are running, for the first part, you start with the open circuit stub, and then you have the piece of transmission line, which is fine in our simulation. If I go back here, if I go out, for the input matching circuit, when I go inside, you'll see we are starting with the open circuit stub, then we have the piece of transmission line. But then for the next part, you are starting with the transmission line, then you have the open circuit stub. If you look in ADS, again, this is your port 1, this is your port 2 for the Smith chart tool. If I go inside, you see that this is flipped. You have the open circuit first, and then you have the piece of transmission line. So I need to reverse these. So there are many ways to do this. One way to do this is delete these lines and reverse or rotate the Smith chart tool itself. I rotated it. So now I have this here. I have this here. Okay, so I just rotated it. So now I know that this is port 1 of the Smith chart. This is where your open circuit stub will be connected. This is port 2 of the Smith chart tool where you have your piece of transmission line. Is this clear? Like, why did I have to flip it?
Professor, that's clear, but in the input matching circuit, when you went into the network, the lengths are a bit different from what we got from.
Yes, they are different because there are always two solutions, right?
Right. Okay. Yes. Right,
yes.
Yes.
So I just selected one of the solutions. I didn't really pay attention whether these are the same solutions we have or not.
Okay.
I agree with you. They're not the same. And I think I maybe briefly just mentioned it. I said, yeah, this is one of the solutions. Okay. And by the way, this is using an open circuit stub. Using the Smith chart tool, you can literally build any type of matching circuit as long as you're going from your load point to your source point. From your whatever load it is, which is 12.6 to the source point. Okay. Let me save this. So this is, for example, 12.3. Now let me run the simulation. See what results, what type of results I will get. Okay, so I got this plot. Now look at this plot. This plot is different than the one that we just obtained, right? It's not the same. But why is it not the same? Because it's not the same solution. But what you'll notice that you are still getting the maximum gain at 4 gigahertz, and it's still 16.7 dB, like you expected. And over here, you're getting also the infinite return loss. And again, this is not the same plot that we obtained earlier. So I go back to this one over here. This is the plot that we obtained using this length of transmission lines. But now we have a different length of transmission lines. At 4 gigahertz, you're still getting matching, conjugate matching, but beyond that, it's not the same, which is expected because you are using one of the other solutions for your problem. Okay? Is this clear for everyone? Now, I'll go one step further, actually. What I'm going to do next, I know I still have one more example to cover, but I want this to be clear to everyone. What I'm going to do next, I'm going to copy this. Just put it side by side. And then I'm going to, instead of using open circuit stubs to do my matching, I'm going to actually do my matching using just normal using normal L network elements. So I'll go back here, go open tools, Smith chart. So Smith chart again, Smith chart. Okay. So this is for the input matching circuit. So I'm going to delete these components. Okay, so this is my load side. I'm going to just lock it. And I'm going to ask ADS to automatically build a matching circuit using lumped elements for me. Okay, so of course it gave me different options. I'm going to choose, which option will I choose? I'll just choose the first one, or maybe this one. Okay, so it created the matching circuit for me. I'll build it. Okay, so if I go inside here now, oh, I didn't like something. Why did it give me an error? Where's the error tool? Yeah, give me an error to check why. Oh, okay. It'll build it using the wrong network. Oh, my mistake. Control Z, Control Z. Stuck. Okay. So it built it using the wrong network. I guess it's fine. So let me delete this for now. So now I'm gonna go Tools, Smith chart. So this is for the second load. So this is 12.6. Again, I'm gonna delete this component. I'm gonna delete this component. I'm gonna ask it to create an lumped element again here, and I'll ask it to build it. So now I'm doing the simulation. So if I go inside here, this is using lumped elements. This is for the input circuit. And this is again using lumped elements for the output circuit, instead of using open circuit stubs. So when I'm done, I press the simulation button and I pray everything works. Okay, here you go. Now, this is how my output will look like. Notice here the following. At 4 gigahertz, we're still getting the maximum gain, which is 16.7 dB, and the return loss is still minimum at that point. But now I'm not using open circuit stubs anymore. I'm using lumped elements. Okay, is this clear? So is this clear for everyone that using a different approach will give you it should give us the same answer at the frequency we're interested in? Is it clear? Okay, great. So now, so I will save this. I will also save this. So you should provide only one solution, Zainab. Okay. You can use a matching network in the assignment if it does not mention what type of network to use. Okay. So just give me 1 second. I have a phone call here and I need to answer it. Or no? Okay. There's no need to answer it. They closed the line. Okay. So Zainab, again, you can use any. You only need to provide one solution. And Ahmad, you can use a matching network in the assignment if you want. But I prefer open circuit stubs really. But you can use a matching network. Now, what is more important for me is that when I ask you to implement the design, I'm not asking you to do the one that is given by the Smith chart tool. It's the one that you're getting from your solution, your own solution, using a Smith chart or not. Okay? So this is example 12.3. Now we can move on to example 12.4. I know, sorry, I'm going to keep you more than expected, but I want to show you as much as possible today. Is it fine for everyone to continue? Yes? Okay. So let me close this window. We're done from this one. Done with this one. And I am done also with this one. So let me just run this one more time here. Just to save the results, because this result was changed when I changed the name of the file.
Professor, this is just like I just had a thought, whether it's possible or not. Can we have like two different kinds of matching networks? One could be like using stubs at the input and maybe L network at the output.
Yes, yes, that's possible. It's definitely, it is possible, right? It is possible because it's a matching network at the end of the day. It doesn't matter how you build it, right?
Yes.
Yeah, you can you can mix if you want. That's fine, but just sometimes you might actually mix them to maximize the bandwidth in some applications. Now let's go to the next example, 12.4. Save this. Okay, close this here. File, new workspace, example 12.4. Now, for example, 12.4, I checked the S parameters. So this is example 12.4. It's asking you to calculate for the maximum, to calculate for you. Let me just read again. Yeah, it gives you the S parameters again at 3 frequencies. In this case, it's unilateral case. S12 is equal to 0, and it's asking you to calculate the gain circles. And again, there's some calculations that you need to do. I would say not using ADS, using your own. You can ask ADS to calculate for you GS max and GL max, but this is really straightforward if you know the S parameters. And you need not to use ADS to calculate for yourself what should be what should be the gain of the source gain circles and the load gain circles. So in this problem, if you recall, we said, okay, you have two options. We have to achieve a gain of 3 dB from the source and the load combined, and then the rest will come from the transistor itself. So for that, we have two options: either the source is S and the load is 0, or the source is 2 and the load is 1, or 1, 2. So really, you can have different criteria. And of course, you need to do the stability analysis first. It's not done here. And again, select against a gamma S and a gamma L, which are as close as possible to the center of the Smith chart. And create your matching circuits and then plot the figure. Okay. So before I move on, I just want to excuse myself for 2 minutes. I just need to make an important phone call, and then when I come back, we will just 2 minutes, and then we will continue on this example. Okay. So I'll keep recording. I'll just mute my mic for the next 2 minutes. Okay, hello. I'm back. Sorry for this delay. So let's move on. First thing that we need to do is calculate the S parameter file based on these values. Okay, so this is what I'm going to do next. So I'm going to go back here to ADS. So let me copy this from here. Or let's start actually fresh. Go to PC, ADS folder. This is the example that we did earlier, so I'm just going to copy it and paste it. I'm going to call it as example 12.4. Then open this using Notepad. Okay, so now I'm going to change the values over here based on the table that we have in the textbook. So for S11, it is still 0.8 at an angle of now 90. Then for S21, it is 2.8 an angle of 100. S12, that's 0 at an angle of 0. S22, that's 0.66, an angle of -50. For 4 gigahertz, it's 75, 0.75 at the angle of -120. For S21, it's 2.5 at an angle of 80. And this is 0. This S12 is 0, 0. And this is 60, an angle of 70. Now this is 71, an angle of 40, 2.3, an angle of 60, and this is again 0, 0, and finally 58, an angle of 85. Now, if you want to make this look neater, you can always play with the spacing. So I can put a space here. I can remove the 2 zeros here. Make it look neater. Okay, so this is the table, and this is example. Just change the name. This is a comment, doesn't matter. This is example 12.4. I save this. Then I go to ADS again. I create a new schematic. I call it as first. I will do the stability analysis first. So example 12.4. Okay, so the same story repeats itself. So S2P file, you ground the middle port, which select, you browse for the file that you need, which is 12.4. You can check it. So it seems like it's fine. There's no errors. It's not reciprocal. It is passivity. No, I think this is related to being glossy or not. Press OK. Then you put your simulation as simulations as parameters. This is again from 3 to 5 gigahertz. And I can select 101 points. Or yeah, we do the analysis first at a single point for stability. This is your input ports. Or before I do the stability, let me check that my S parameters are correct. So I go to linear scale, 3, 5, okay, and step of 1 gigahertz. Okay. So I'm just loading. I just want to look at my S parameters really. So now I just want to look at my S parameter files. So S11, all of these, add, rearrange them. Okay. So these values here should match the ones in this table. Okay, so 0.8 at an angle of -90 and so on. Yeah, they match. Okay, so this means that creating the S parameter file is correct. So next, let me do the stability analysis at 1 frequency. So again, for stability analysis, you can add your mu, you can add your K. If you want, you can add your noise circles just for the sake of this example. So I can say noise circles here, load circles there. And you can say the regions. And you can run this result. Okay. So this will give you at 3 frequencies, but I want to do it only at 1 frequency. So again, single point, 4 gigahertz, press OK, simulate. So again, I can plot my mu and k factors. So mu, k, says the stability factor k is invalid. I'm not sure why it gave me this error. Why? The mu factor is indeed greater than 1. Now my delta factor, it gave me an error. Maybe because S12 is equal to 0. Yeah, probably because it's infinity. Yes, yeah. Probably k will be infinite because S12 is equal to 0. If we look at the equation of k, this is why it says it's invalid. If we look at the equation of, yeah, you're dividing by 0, exactly, which means that it is stable. If the answer is infinity, this means it is stable. So if we look at the factor, yes, it is here. Yeah. If you look at k is equal to this, divide by S12, S21. S12 is 0, so 1 over 0 is infinity. This is why ADS told me that you have an invalid answer, because it cannot display infinity. Okay, so this is good. Now, if you look at the stability circles and the stability regions, so for the stability circles, you need a Smith chart. Stability circle 1 for the source and the load. And in plot options, again, I'll make the maximum 1. And it is empty. When it is empty like this, this means that my stability circles are totally outside the Smith chart. As for the regions, load region and source region, both of them should stay outside. Yeah, this means anywhere in the Smith chart, you'll be stable. I mean, we don't really need this because we know that my circuit is unconditionally stable already. Okay, this is what the K factor tells me. Now, you do your calculations to calculate what should be the source and load gain circles, and you can plot them. So if I want to plot them, so let me file save as on this gain circles, or maybe not. I'll just keep it as it is, cancel. Okay, so to plot the gain circles, you have the following options. So you have gain source circles and gain load circles. And also this can be found in your in the tutorial. So this is the gain circles. Not you need to input, you need to figure out how should you, if you look at the not a tutorial, at the example, we said you have multiple options, GS or GL, 3 and 0, or 2 and 1, or 0 and 3, or 1 and 2. So you have multiple options. You have 4 options really. So we will just go with the 2 ones which are here, 3 and 0 and 2 and 1. So how do I plot these gain circles on the Smith chart? So I go back to my schematic. What you need to edit is, let me go to gain. What you need to edit is this number over here, 2. 2 represents the gain of that circle. Okay. Now in our example, we have 2 gains. We have either 3 or 2. So how I'm gonna show this in ADS now? How I'm gonna plot this using ADS? Now over here, you put you open a curly bracket and you enter, what did we say? Sorry, I have a fish memory. We said 3 or 2. So I put 2 and 3. And then the last number, 51, this indicates the number of, this will indicate the number of points that you will have on that circuit. Okay? So you can keep it as it is. You don't need to do any changes there. You press apply. Okay. Now for the load circle, it's the same story. We said that if you have a gain circle 1, then you have 1. If your gain source is 2, then your load circle is 1. If your gain circle is 3, then your load circle is 0. So I'm just going to say 1 and 0. Then you are done. Then I run the simulation. Now, again, using a Smith chart tool, I can plot these gain circles. So GL circle and GS circle here. So add them. Again, plot options. Make sure your Smith chart does not auto scale. Press OK, and you get these circuits. Okay, this is for, and these are the same circles that we have in the also in the notes. So if you go back to the notes, I think the solution maybe, yeah, over here. This is the Smith chart. So these are the ones in green and red. In this case, the one is in blue matches the one in green, and the one in red matches the one in red, also in the Smith chart. Okay, so this is how you plot your gain circles. Now, next is you need to choose your gamma S or gamma L on this gain circle, which is closest to the center of the Smith chart, and you can do that using a marker. So you can just put a marker or any of these circles, and you try to choose the one which is closest to the center of the Smith chart. So this is for which gain circle? This is for gain circle equals to 2. So can you choose which one is closest? So the one which has the smallest, you need to look at this number, the one which is closest to 0. So 0, 4, 5, 3, 7, 3, 7, 3, 7, 3, 7. So I think it will probably be maybe this point, 0.337 at an angle of 123. Okay, so do we have the values somewhere? Yes, I'm looking at the solution. Just actually at the bottom, it's written here for gamma S, which shows 0.33 at an angle of 120. When we choose the 2 dB circle, it's actually in purple over here. This is the one that I'm referring to. And again, we're using the marker. When you put the marker, it will tell you what's the gain of the circle. And it will give you gamma S on top and the equivalent impedance normalized or multiplied by the reference at the bottom. So if I'm going to use the 2 dB circle, then for the load side, I need to use the 1 dB circle. So again, I can insert another marker, and this is not the correct one. So now this one is in the 0 dB load circle. So I need to move it to the other one. So as I need to move it to this circle, again, let me put this at the bottom so you can see it. Now, again, I need to get as close as possible to the center of the Smith chart. Again, look at this number, 0.2023. It should be as small as possible. So 1.727, so yeah, 0.217 at an angle of 74. If you look here, the answer is 0.22 at an angle of 70. So it's very close to what we expect. Is it clear how I obtained these numbers using ADS? You try to find the numbers which are the closest to the center of the Smith chart, and of course, you select it on the corresponding gain circles that you are after. What about the rest? Now, your next task is to take this value. This is gamma S. So you take the conjugate of this gamma S and you create your input impedance matching circuit. This will represent your gamma L. You take the conjugate of it and you create your output matching circuit. Okay, this is the next step that you need to do. Again, how can you create your input and output matching circuit? You can either do it analytically using any of the matching techniques that we learned, or you can do it using a Smith chart, or you can do it using the Smith chart tool that I showed you just earlier, like half an hour ago. So it's up to you how you want to do it. Okay. Now, let's say you created your Smith chart and it matches the one which is in the notes over here. So let's build this again and see if we can obtain the same plot on the other side. So let me save this. I'll close this now. So before I move on, so any questions up to this point about all of these blocks I'm using? Ahmed and Zainab, is it okay? Okay, so now I'll say save as here, file, save as. Now I'm gonna create a new file called matching. I don't need these again really, so I'm gonna just delete them. And I will create my matching circuit. I'm gonna do that again using idle transmission lines. So I have 1, 2, 1, 2. This is your input and output matching. This is your S2P file. Then I use lines here. Okay, great. Now I need to adjust. The impedances are all 50, but they are 50 at the center frequency, which is 4 gigahertz. Again. And now I need to adjust the length. So the length, again, you need to write it in degrees. In the slides, they're given in lambda. So for the first one, it is 0.10 times lambda, which is 360. So this will be 36 degrees. Okay, next one, this is 0.179 times 360. This is 64.44. Next one, this is 0.045 times 360, 16.2. And the last one It is 0.432 times 360, 155.52. Okay, we are done. So this is your full network with the input and output matching. Okay, so you can always draw a shape to indicate this. This is input matching, output matching. Now I can run the simulation. Okay. Where is the mistake? I need to run the simulation, the linear scale from 3 to 5. Okay, so I will plot, again, I will plot the S11, which will represent minus my return loss, and S21, which will represent my gain. And I will plot both of them in dB scale. And okay, and we get the following plot. And now compare this one to the one we obtained here. Aren't they the same? What do you think? Yeah. Great. So this is using again circles. So any questions? So again, for the gain circles, if you're not doing it for maximum gain, you have to go through all the steps first and determine what should be your gain circles, like which gain circle, and then based on that, as we have seen in some of the results, so maybe I can open this again here. Then using the Smith chart, you can select your gamma S and gamma L. You take the conjugate of that, and then you design your impedance matching circuit. So now, the last thing I have to you here is example 12.5, where you are using where you have to calculate the noise circles, and I think here you have to do that for maximum gain at the load side and maximum gain at the load side, I think, and for different gamma S's. So let's work this problem out. So let's see. So I will save this again here. Let me close this. I will save this, close this, save this, and also close this. And file. Create a new workspace. I call this example 12.5. And create a new schematic. Example 12.5. Now over here, if you look at this example, you are given the S parameter files at only a single point, not at multiple points. So you might as well also not use an S2P file here. You can use an S2P file if you want, but you don't need really. You can use the the linear equation. So again, if I go to equation-based linear, I'm going to use this block. And I need to enter the values of S11, S1221, etc. So starting with S11, again, it is 0.60 at an angle of minus 60. So this will give me 0.3 minus J times 0.52. For S12, it's 0.05 at an angle of 26, which is 0.045 plus J times 0.022. Then you have S21, which is 1.9 at an angle of 1.8, which is 1.90 plus J times 0.059 or 6. And finally, S22, 0.62 at an angle of 100, sorry, no, not 62, 0.5 at an angle of minus 60, 0.25 plus J times, no, minus J times 0.433. As for the reference impedance of the two ports, that's 50 and 50. Now you ground the two bottom ports. Then you use simulation as parameter again. I'm doing the simulation again at a single point, and this point in the question is given as 4 gigahertz. And I put my terminals at the input and at the output. Now the question here is asking, for design purposes, assume the device is unilateral and then design an amplifier that will have a 2 dB noise figure with a maximum gain that is compatible with the noise figure. Okay, maximum gain. So we said that the noise figure circles, if you are given the noise figure itself 2 dB, then you need to plot the corresponding noise figure circle. So to plot the corresponding noise figure circle, you need to use this option over here. It's called NS circle. So I plot it here. Now in this NS circle, you have different input parameters that you need to enter: NF2, noise figure minimum, S-opt, etc. So let me double click on this. Starting with NF2, this is the noise figure that you're designing for. So in our case, we're designing for a noise figure of 2 dB. So we need to plot the noise figure circle at 2 dB. Noise figure minimum, this is the one given from the manufacturer, and also in the question, it is written as 1.6. S optimum represents the gamma for the optimum gain, or the optimum minimum noise figure, and you need to enter this in rectangular form. In the question, it is given as 0.62 at an angle of 100. So in rectangular form, this is equal to minus 0.11 to 2 decimal places again, plus J times times 0.61 minus 0.11 plus j times 0.61. Then you have Rn. Rn again is the normalized impedance at which gamma opt was calculated, and in the question it is given as 20. So 20 is divided by that 50 number, and then you are ready. So that's it. So then you have 51. This is the number of points that you're going to plot on the noise figure circle. Press apply, press OK. So this will plot for you the noise figure circles. Now, as we discussed in class, when you plot the noise figure circle, you want to calculate for a certain gain, you need to see the intersection of the noise figure circle at 2 dB with the gamma S circles. Okay? What about gamma L? Gamma L will be automatically designed because the question is telling you that gamma L will be selected for the maximum gain. And based on that, you need to calculate what is gamma L for maximum gain, and so on. But for gamma S, which is the source, no, you need to plot the gain circles. And when we solve this question, we said we're going to plot the gain circles at 1, 1.5, and 1.7. So you can do the same thing here. You plot the gain circles. Again, this block. And this is done at 1 dB, 1.5, and 1.7. When you plot these, what you are looking for is the intersection of the noise figures with the gain circle that will give you the maximum gain, with any of these three gain circles, but the maximum one. So let me add more circles here. Let's say I add a circle which is at 2, at 2.5. Maybe I'll add a circle at 0.5. Just more circles. Show you how this will look like. In the example, you only did it at 3. I'm just adding more here because why not? We can do that. Next step is to do the simulation. Okay, now I plot my gain circles. By the way, one thing which I skipped over here before I plot the circles, I did not do the stability analysis, for example. So you need to do this maybe. And maybe if it is unconditionally stable, you need to plot the stability circles and check the stability regions. So you need to do all of these things if necessary, if your device is unstable. Now back to the noise circles, we have the gain circles here and we have the noise circles here. So I add it, press OK, and I can see only one of them. Where's the... This is the noise circle. That's fine. What is my gain circles? Did I do a mistake somewhere? Oh, okay. Maybe it's outside. No. Anyone has an idea where my gain circle disappeared? Oh, okay. I know what's the mistake. I know the mistake. I think someone wants to tell me what's the mistake. My mistake is that I wrote these gain circles in the wrong place. I should take all of these and replace it here. Sorry, my mistake. So this should remain as S, and then the gain circles are over here. So press OK again, and the simulation again. Okay, here you go. So let me expand this a bit. Let's have a look at it. So these are, again, the blue one is my noise and the red ones are the gain circles. So what I'm looking for is an intersection where you'll get the maximum gain. So let's start with the outermost circle. or the biggest circle we have here. This circle has a gain of, this one I have the mouse on, has a gain of 0.5. And you can see there is 2 intersections for the noise. So since we want to design for maximum gain, we know we can do better. So we go to the next gain circles. The next gain circle is at 1 dB. Again, there is 2 intersections. Maybe we can do better. So we go to 1.5. At 1.5, we have also 2 intersections. Maybe we can go better. So we have 1.7. At 1.7, if I zoom in, trying to zoom in. At 1.7, if I zoom in, I have intersection at 2 points also. So if I increase the gain by a bit, I can get exactly 1 intersection. But maybe it's not as easy to do if you're doing it manually. But in ADS, you can do that. But then if you look at the inner circles for the gain circle of 2 or 1, sorry, I need to expand this. If you look at the gain circle inside, this is the gain circle of 2 dB, 2.5, and then in the middle it's 2. So really the best circle we have is the 1.71. So you need to select the intersection point. So I can add a marker, new marker, and I can maybe zoom in. And then take the marker and try to move it around. So I will maybe get this intersection point. There are 2. Maybe I'll select this one. This will give me a gain of 1.7 and the 2 dB noise figure I am after. And then this will give me the value of the noise figure circle. If I want to calculate it from the gamma S, I need to put the marker on the 1.7 dB circle. So let me try to move it. Not move it. Let me delete this marker. So marker, new, I'll put it in the 1.7 circle. So here. So again, move it, move it, move it, move it, until I get again the same intersection point, which is here, almost here. Somewhere here. Okay. So in this case, my gamma S will be 0.511 at an angle of 74. And this will represent a gain of 1.7 dB with a noise figure of approximately 2 dB. I'm looking at the solution we have. Now the solution that we have gave us a gamma S equal to gamma S. Where did I read it? A gamma S of 0.53 at an angle of 75. The answer 0.53. The answer we're getting here is almost the same, 0.51 at an angle of 74. Okay. Now, if the question specifies for you a certain gain, not the maximum gain, but a certain gain, then what you need to be after is the intersection points between the noise figure circle and the gain circle. For example, this point. Let's say that the question is telling you that the source gain circle is 1 dB. So then you go with the intersection point, which is closest to the center of the Smith chart, which is, we have 2 of them, either this one, I mean, we need to make this more discrete, or this one here. In that case, if you want a gain source circle of 1 dB, then your gamma S will be 0.324 at an angle of 92. Then, of course, the next step, you take the conjugate of gamma S and then you build the matching circuit. For the load side, it does not care much about what is the noise figure circle, but what cares about is what's the value you want for the load side. Are you doing the maximum gain for the load? Are you doing it for a certain gain? The same story that we did in the previous example. It repeats itself. Of course, in all these cases, we're assuming that we are in the stable region of the transistor. Okay, so this is something that you always need to check for. And that's it really. So what we did here is the 3 examples. So what is left for you is to design the matching circuits, and this is what is also done in the examples in the notes. Okay. So any questions? Any questions? So I hope this will help you in solving the assignment. Okay. So please, through that, thanks everyone for your time, and thanks Majid for giving us that hint about the new element. This is the first time for me to learn about it. So please practice using your assignments. It's a very good way to learn all of this. And again, there is always more that you can learn about ADS. Okay, I tried to summarize some of the things that you need in this course. Before you leave, just one last thing. Let me open one of the previous examples we had. Just want to talk about one point. I think it was this workspace. I think it was this one. Now, what I want to mention here is, again, has to do with designing these transmission lines. Sometimes in the question, I might give you a certain substrate, a microstrip line, and I will ask you to design it based on the microstrip line. So how do I approach this problem then? In that case, you need first to use the information you have about the microstrip to calculate what's the width of the microstrip line and what's the length of the microstrip line. How do you calculate the width? We have the equations. What about the length? To calculate the length, you need to find the effective impedance, the effective permittivity, and you have to find the wavelength, and then convert everything to millimeters or meters. So what do I do after that? In ADS, you don't use idle transmission lines anymore, but you use microstrip transmission lines, the second option here. And for that, first you need to define your substrate. Okay, this information will be given for you. And then you can add a piece of transmission line. You define the name of the substrate, the width and the length, and the same story if you have an open circuit transmission line. Okay, well, I will not do this over here, but this is what I think in the exam, midterm exam, some students, in some problems, they do not use the microstrip line, but they use the transmission line instead for some questions. So just be careful about this. Okay. So that's it. That's everything that I have to offer you. So that we will, inshallah, meet on Tuesday morning, please. And then we will have your presentations, hopefully on Tuesday evening. For the presentation, for the submission of the final report, you can do that after the presentations. Okay. And again, as we discussed, your final exam will be given to you on the 28th, I believe. It will be a Tuesday, and then you'll have 2 days to complete it. Okay. Any questions? Yes, of course. You can postpone it to Thursday. That's not an issue at all. But please try your best. Give your assignment your best. Okay. Like using ADS, using MATLAB as required. Okay, please. Because it will also be a good practice for you for the final exam. Okay. Welcome. So that's it. So thanks everyone. And now I have to leave you. Probably I have to go. Let me stop the recording.